Hello, this is Math Jazz from Almost Cool. So we had a false start. There we go. Hello, this is Math Jazz from Almost Cool, and I am here for Friday's math live stream. I have these every Monday, Tuesday, Thursday, and Friday at 5 p.m. Mountain Standard Time. So, with that, yesterday we talked a little bit about nowhere dense sets and meager sets. Today I want to continue talking about that. Of course, if you have your own questions about math, then you can type them into the chat, or you can either email them to me at mathjazz9@gmail.com. So if you email them to me or if you put them into chat, then I will answer them. But today, in fact, I'll put that into chat right now. Email address, mathjazz9@gmail.com. Okay, so, yes. Today, we're going to continue with what we were talking about yesterday, which was about, well, a little bit of descriptive set theory. We're talking about nowhere dense sets and meager sets. So, let's switch to our camera, and let's remind everyone what these were. So, nowhere dense. There we go. N is nowhere dense if for all open U not equal to the empty set, so all non-empty open U, there exists open non-empty B contained in U such that B intersect N is the empty set. This is nowhere dense. Then meager was the other thing we talked about. Meager is M is meager if M equals the union of countably many dense sets. Okay. Now, I think that yesterday we proved that Q is meager in R. So, today we're going to talk about something called co-meagerness, and we're going to get into homeomorphisms and almost homeomorphisms. So, co-meager means that M is co-meager in X if X minus M is meager in X. So it turns out that something can be the same set can be meager in one space and non-meager in another, or nowhere dense in some space and not nowhere dense in another space. So let's give an example of that, because that is important. So here's our new sheet of paper. We'll have, for example, we showed yesterday that Q is meager in R. But we're going to show that Q is not meager in itself. Actually, it is meager in itself. We showed that N is meager in R. There we go. We showed both of these yesterday, I'm pretty sure. So we're going to show that N is not meager in itself. Okay, so N, of course, is equal to set 1, 2, 3, 4, and so on. All of these points are separated from each other. There we go. All of these points are separated each other like this in our space. This is N. Now, I want to show that any arbitrary point is going to be the singleton set containing it. So the set that contains only that point, for example, this set, it contains only this point of N. That is not nowhere dense. So the definition of nowhere dense is for every open set, there is, so for every open set U that's not empty, there exists an open set V that's also non-empty, and V is contained in U, such that V intersect N is empty. So, if I have this set here, N, I claim that this set N that contains only this point is not nowhere dense. I guess the opposite of the opposite of nowhere dense is somewhere dense. So we're going to call it that, somewhere dense set. So if I let U equal N, well, this is an open set. And so I'm picking U equals N. So I have my set N. It's I have my set N that I'm trying to prove is not nowhere dense, to prove it is somewhere dense. I have U equal to N, so that's the same set. And now, if N were nowhere dense, I would be able to find a non-empty open V in U such that V doesn't intersect N. Well, the only non-empty set inside of U is U itself. And U intersects N. So that means that all of the subsets of U either intersect N or are empty. So I can't find a valid V. And that is going to prove that N is somewhere dense. Okay, now I did this to an arbitrary point of N. This works for all points in N, so therefore every point of N is somewhere dense. Okay, so there's no subset of N, except for the empty set, that's nowhere dense. Well, how am I going to get a union of meager sets? Sorry, how am I going to get a countable union of nowhere dense sets to get a meager set that equals N? Because that was the original goal, was to prove that N is not meager in itself. If N were meager in itself, then I'd be able to find countably many nowhere dense sets such that their union is all of N. But every point is somewhere dense. And you can't have a nowhere dense set containing a somewhere dense set. Put it the other way around. you can't fit a somewhere dense set inside of a nowhere dense set. So there's no countable union of sets that unions up to n inside of n, because every point is in its own singleton set that is somewhere dense. So there's no way to get any of the points inside of n into a meager set, because none of them fit into a nowhere dense set, and a meager set is made of nowhere dense sets. Oh well. So n is not meager in itself, but n is meager in Q, and it's meager in R. Okay, so co-meagerness. Co-meagerness was, if some set is meager, then its complement is co-meager. So this is going to lead us to our definition of almost homeomorphic. Okay, so X and Y, these are both topological spaces, are almost homeomorphic if there exists co-meager A in X and B in Y, such that A and B are homeomorphic. So that's what almost homeomorphic means. So we're going to introduce something called a Baire space. Okay, we're going to talk about how almost homeomorphic is an equivalence relation on Baire spaces. So the relationship X and Y are almost homeomorphic to each other is an equivalence relation on Baire spaces. So okay. So what is a Baire space? A Baire space is a space such that the interior of a meager set is empty. So that means that, in particular, if X is Baire, then X is not meager. That's the important part. Not meager in itself. Okay, so we're going to prove that almost homeomorphic is an equivalence relationship on Baire spaces. So the first two steps are not too hard. Remember, an equivalence relationship has to be reflexive. The order doesn't matter, but this is the common order. Reflexive. So that means that X is almost homeomorphic to itself. 2 is we want symmetric, which means that if X is almost homeomorphic to Y, then Y is almost homeomorphic to X. And we want transitivity. That means that X related to Y and Y related to Z implies X related to Z. So this equivalence relation is something that is massively important in mathematics because basically it generalizes what we mean by equals, like um, equality is an equivalence relation because it satisfies these three things. But there are lots of things that we can think of as equivalence relations that aren't exactly equals. Similarity of triangles, for example. Every triangle is similar to itself. If one triangle is similar to another, then the second is similar to the first. If two are similar and another two are similar, so like A is similar to B and B is similar to C, then A is similar to C. So triangle similarity is an example of an equivalence relation. But it allows us to define when things are equal enough for our situation at hand. So in uh, so almost homeomorphic, there are certain classes of spaces that are almost homeomorphic to each other, even though they're not the same space. The fact is that they are the same in this way. They're the same in that they are almost homeomorphic to each other. So if we can prove some property works for, there are times when we can prove that a property is preserved by almost homeomorphisms, meaning that if one space has this property, then all spaces that are almost homeomorphic to the space also have the property. So being able to prove that almost homeomorphic is an equivalence relation allows us to make statements like this. Okay, so we're going to prove that almost homeomorphism is an equivalence relation on bare spaces. Okay, so first thing we need to do is prove that every space is almost homeomorphic to itself. So that's the first step. We're going to prove reflexivity. So X is comeager in itself. And X is homeomorphic to itself. So there's a comeager subset of X, namely X, that is homeomorphic to a comeager subset of X, namely X. So X and Y, so X is almost homeomorphic to itself. You're thinking, well, how do I know that a space is comeager in itself? Well, the empty set is nowhere dense, meaning that the empty set is also meager, because every nowhere dense set is a meager set. So that means that the complement of the empty set in X, since X is a meager set in every space, since the empty set is a meager set in every space, then the complement of the empty set in a space is that space. And comeager just means the complement of a meager set. So every space is the complement of the empty set in itself. So every space is comeager in itself because the empty set is always meager. Okay, so that proves that we have the first property, reflexivity. Number 2. We have symmetry. So if X is almost homeomorphic to Y, then there exists A in X and B in Y, such that A is homeomorphic to B. But that means, since homeomorphism is already an equivalence relation, that means then B is homeomorphic to A, so Y is almost homeomorphic to X. We haven't needed bare set yet. Turns out that almost homeomorphic is reflexive and symmetric on all topological spaces. It's just not transitive on them. So it's almost an equivalence relationship on all spaces, but it's just not quite, because it's not transitive on non-bare spaces. And we'll have to prove that. But I want to finish proving that this is an equivalence relation on bare spaces. Then I'll prove that it's not an equivalent space, or sorry, not an equivalence relation on non-bare spaces. Okay, so 3. We want to show that if x similar to y and y similar to z, then x similar to z. Okay, like that. So we want a in x, b in y, c in y, and d in z, with a homeomorphic to b and c homeomorphic to d. Unfortunately, we don't get that b and c are the same. Knowing that x and y are almost homeomorphic means that there is some comeager subset of y that's homeomorphic to a comeager subset of x, and knowing that y is almost homeomorphic to z gives us the same thing between y and z. But it does not give us that it is the same comeager subset of y homeomorphic to x as homeomorphic to z, which is a bit of a drag. But that's okay. We can handle it. So what we know is that B intersects C is comeager in Y. We get that because X, Y, and Z are bare spaces. Okay. So I said this part only works. This third part only works if X, Y, and Z are bare spaces. So if B intersects C is comeager in Y, then that means that since Y is a bare space, that means that B intersects C is comeager in B. So there's a function that's a homeomorphism between A and B. Let's say this is what our homeomorphism is. We're going to give it a name A. This implies that F inverse B intersects C is comeager in A and comeager in X, and this is a comeager subset of X that is homeomorphic to this comeager subset of Y. So that means that well, we can now use this B intersects C as to construct in the same way. We have a homeomorphism from C to D. Okay, we know that G of B intersects C is comeager in Z. Okay, so this set is homeomorphic to this set, and homeomorphic in turn to this set. So this one in X is homeomorphic to this one in Y, which is homeomorphic to this one in Z, which means, because homeomorphism is transitive, that this set is homeomorphic to this set. So this set of X is homeomorphic to this set in Z. Further, this is comeager in X, this one is comeager in Z, so X is almost homeomorphic to Z. Okay, so that proves that for bare spaces, we get the transitivity relation that we were looking for. But I claim that we do not get this for non-bare spaces. So this is a very concrete example. Let x equal a single point 0, y equal q, and z equal, I want to use z equal the integers. So z, the space, equals z, the integers. Like so. Okay, so I claim that x is almost homeomorphic to q, and q is almost homeomorphic to z, but x is not, so the slash through it means not, almost homeomorphic to z. This is how we do this. So, first of all, every subset of Q is meager in Q. So, every subset of Q is comeager in Q. Okay, so how do I justify this? Well, since every point of Q is nowhere dense, and Q is a countable set, that means that every subset of Q is at most a countable subset of Q that is a union of singleton sets, that is a union of nowhere dense singleton sets. So every subset of Q is a countable union of nowhere dense sets. So every subset of Q is meager. But if every set is meager, that means the complement of every set is comeager. So every set is meager. Every set is the complement of another set. And that set is meager because every set is meager. So every set is the complement of a meager set. So every set is comeager. Okay, so every subset of Q is comeager, which means that if I draw the homomorphism, here's a homomorphism from 0 as a subset of X to 0 as a subset of Q by f of 0 equals 0. This is a homeomorphism. It sends one point to one point, therefore every open set of that point is sent to an open set of that point, and every open set of this point is drawn backwards to an open set of that point. That it is a homeomorphism. But every space is comeager in itself, so X is comeager in itself, and every subset of Q is comeager in Q. So this is a homeomorphism of comeager sets, so therefore our singleton set singleton set 0 is almost homeomorphic to Q. Now, I claim that F, let's use a new letter, G from the integers living inside Q to the integers is a homeomorphism as well. So Q contains a nice copy of the integers inside of it. So, and every subset of Q is comeager in Q. So this is a comeager subset of Q, and it's homeomorphic to Z, which is a comeager subset of Z. So therefore, this is a homeomorphism between comeager subsets, so Q is almost homeomorphic to Z. Okay, so that's fine and dandy, but we proved that no non-trivial, that is, no non-trivial subset of Z. Non-trivial means it has at least a point in it, so no non-trivial subset of, and I mean Z is the integers, no non-trivial subset of the integers is nowhere dense, which implies it's non-meager. Well, every subset of Z that isn't Z, so every proper subset of Z, that is, it's at least 1 point smaller than Z. There's at least 1 point of Z that's not in it. Its complement is, well, at least that point that's not in here. Let's draw this. So here we have Z. Here's 0, 1, 2, and so on. Here is Z, the integers. So, if I have some set that misses some point, say it misses at least this point, maybe it misses more than that, okay? Then the complement has that point in it. The complement having that point in it means the complement isn't nowhere dense, means the complement isn't meager, which means that the original set was not co-meager. So if A doesn't have the point 1 in it, then A complement has the point 1 in it, and that means A complement is not meager, so A is not co-meager. So the only co-meager subset of Z is Z, because Z's complement is the empty set, and the empty set is always meager in every space. So that means that there is no subset of Z accepting Z the whole thing that is co-meager in Z. And you're wondering, well, why is that a problem? Well, we need to have a homeomorphism between the singleton set 0 and a co-meager subset of Z. But the only co-meager subset of Z is itself. So can we get a homomorphism from the singleton set 0 to all of Z? The answer is no, because homeomorphisms are bijective. Bijective means, of course, that the two, your domain and codomain have the same cardinality, but this has a cardinality of 1. There's one element in it, and this has an infinite cardinality. So this has way more than one element in it. So these two sets, because they do not have the same cardinality, cannot be put in bijection with each other. So even though singleton set is almost homeomorphic to Q, and Q is almost homeomorphic to Z, we cannot find a homeomorphism between co-meager subsets of 0 and Z. This is impossible. And that is our live stream for today. So we hope that you enjoyed learning a little bit about descriptive set theory. Next week, we will start talking about matrices again. My students will be learning about adding and multiplying matrices, so we'll get back to that. If you have questions, please email them to me, and I will answer them in the next live stream on Monday. So hope you're enjoying learning math. Have a great day. Thank you for watching, and here again is my email on the screen for you to email your questions to. Bye!